Great. I, well, welcome back to the first session of our spring ARN Seminar series. Yep, please take it away.
Okay. So yeah, thanks a lot for giving us this possibility to tell you about our work. It's really a great community that you've put together, and I'm hope that we'll be able to participate more regularly in the future. So we'll tell you mostly about a paper that's currently under review entitled Thermodynamic Consistency of Autocatalytic Cycles. And Thomas, who's just on my left now, will give you a lot of the details of the paper. I will focus more on the parenthesis part of the title, how could natural selection emerge from physics? So it basically gives you some background information on why we started studying these questions and where we want to go in the future. So, and this work is conducted with Denis, who's probably going to be online very soon, and Etienne, who's in the room with us as well. Okay, so the place where we come from is evolutionary biology, at least part of us. I'm an evolutionary biologist, Etienne as well. Thomas is a physicist, and Denis is a mathematician. And we started thinking about this project a few years ago, trying to understand what it would take to understand Darwinian dynamics in a very general sense. And to do this, we basically asked ourselves as evolutionary biologists, what are the conditions for evolution by natural selection? And this is what we come out after thinking about it. We need some kind of entities that can produce copies of themselves. Sometimes there can be mistakes, so some kind of variations in their properties. But some variations are of particular interest because they can be transmitted over generations. And this is what biologists tend to call mutation. So basically, the three properties that we need for typical evolution by natural selection to take place is individuality, reproduction, and mutation that produces heritable variants. And if you've got this heritable variants, then as evolutionary biologists, well, basically we can explain the rise of biodiversity as we can see it on Earth. The problem we're trying to address now, which pertains not only to the origin of life, but also basically to trying to understand any kind of Darwinian dynamics from a physical perspective, is to try to clarify how these properties come to be in a physical perspective. And if you ask yourself, how did that happen? I think it's interesting to realize that there are two big families of perspectives on this problem. One that we would call just luck, and the other that we call dirty Darwinian dynamics. So the question is, okay, how did the first part of this picture arise? One explanation is that, well, some entities able to do all this arose. Typically, they could be self-replicating RNAs. And importantly, it's supposed that they occurred at a given time point, and they didn't occur by natural selection, because by definition, natural selection occurred after this event took place. So in other words, before this, there was no evolution by natural selection. In our opinion, it's a bit problematic to see things in this way. Many of you are probably aware of the difficulties that these typical RNA first hypotheses are encountering. And our opinion on this problem is that, well, probably the conditions for evolution by natural selection have not been properly described when I did that earlier. And it would be possible to get evolution by natural selection in a dirty way, and that would participate to the explanation of the emergence of these particular objects. So this is our perspective. We're trying to understand the gradual emergence of these processes rather than their sudden emergence. And to do this, we decided to use modeling and to basically start from scratch. That is, to not assume any complex properties to start with. We just assume a well-mixed physical soup. We call it a physical soup in reference, obviously, to the chemical soup, but we call it physical because we would like our models to be more general than just chemistry. Although at the end, we still suppose the existence of entities that could well be atoms or molecules, if you like. So we suppose a system where we have primary entities that get in the system, and there can be various categories of them. Here we have two categories. So they get in the system at constant state, which means that the systems, our models, are out of equilibrium. And we let these things associate and dissociate. And we suppose that the resulting entities are only compositional in the sense that, so it's not real chemistry. We don't pay attention to the steric organization of the component. It's just the number of gray and white that you have that matter to define your properties. And we do this by taking care of the thermodynamic constraints that we want to respect in doing this through Gibbs free energies, activation barriers, and mass action. And one interesting thing that came to us, which actually came to us a bit as a surprise, probably not to many of you that have thought about these issues before, is that we have very interesting phenomena occurring right away just with this very simple setup, catalysis and autocatalysis. And you're probably not going to learn much here, but just wanted to make sure that we're all on the same page. Catalysis simply occurs when some components get in reactions and out of reactions, and in doing this, allow a faster production of something. So here, for example, this chain of reactions can be summarized as the B component, the B entity, catalyzing the ligation between two A's. And if you've got catalysis, well, for the same price, you can have autocatalysis, which is a situation where the product of the reaction is the catalyzer, is the catalyst itself. And then the autocatalytic cycles can be described in this typical cyclic way. And at that stage, I will let Thomas get into give you the details, and I will come back at the end of the talk. So I will stop sharing, cut my sound.
Thomas, your mic is not on yet.
C'est là.
Ouais, c'est bon.
Yeah, that's working.
Can you hear me now?
Yeah.
Yeah.
Etienne, tu Can you hear me? Okay.
On peut.
Okay. Sorry for this technical aspect. So yeah, just to follow up on what was saying Sylvain, just to make sure we're on the same page. So not as a big surprise, we rely on the results from Alex that was published some years ago. That is, it defines autocatalysis in a purely topological grounds. And that's something we like. So it means that we have a reaction networks, and in fact, we describe it with a stoichiometric matrix, okay, where lines represent the entities and currents the reactions. And in fact, in this formalization, looking for autocatalysis means that you're looking for a submatrix of this whole stoichiometric matrix, for which there exists a vector of flows for the reactions, such that the matrix products with S cycles and phi gives only strictly positive components. So this is a mathematical translation of this idea of self-amplification, right? Because S cycles times phi is just the time derivative of the entities that are contained in this submatrix. So there are a few other conditions, but I don't go into details. That's the most interesting part to what I want to say today. So, and for the rest of the talk, we will focus on minimal autocatalytic cycles. So simply cycles that do not contain any others. And we call them autocatalytic cores, sticking to Alex's terminology in his paper. So in our paper, which is under review, we have, there are two families of results. The first one is about the computational complexity of detecting those autocatalytic cores. So it has been already suspected in the literature that detecting such cores would turn out to be an NP-complete problem, okay? Such as in this paper of Peng et al. And if that's the case, it means that we need to implement the appropriate tools in order to detect autocatalysis in reaction networks. So that will be the first part of the talk. And then I will focus on the realizability of those detected cores under mass action kinetics and thermodynamic constraints. Okay? So let's start with the computational complexity. So there's a bit of, when we talk about NP-completeness, what we think of the most famous NP-complete problem is the SAT problem. So NP-completeness is it's a class of computational complexity, which means non-deterministic polynomial for technical aspects. And so typically in the SAT problem, you have clauses, you have a formulation that's phi, and you have various clauses that you want to find solutions of them, for all of them. And each clause is composed of literals, and you want at least one of them to be true. Okay, and so typically how you can think about it is you want to throw a party and you want to invite some people that we call x1, x2, and x3. And so the first clause is here tells you that you want at least one person in your party, okay? And the second clause tells you that x1 and x2, they don't get along. So at least one of them should be missing. And so you look for a solution of that. And that kind of problem we know is NP-complete. And the nice thing is we know that NP-complete problems, they are all equivalent. So it means that the SAT problem has been, people have been working on this problem for a long time. And so it means that if detecting cores is NP-complete, then we can use SAT solvers in order to detect autocatalysis. And that's good news for us. So autocatalysis has been suspected to be related to completeness for a while now. I think it started with the RAF theory, which is known to host NP-hard problems. But in the RAF theory, it's very different from the problem we're addressing here because we assume catalytic interactions between entities in a system, and this is how autocatalysis emerges. But in our reaction networks, we don't assume such catalytic interactions between entities. So autocatalysis just emerges spontaneously in this formulation by Alex. And there's another paper which is cited a lot, this one from Anderson, but actually the NP-complete part, what was really hard in their problem is this output maximization in a reaction network, not so much the detection of autocatalysis. So it turns out that detecting autocatalysis a la Bloquist still remains to be addressed. And so we answer this question in this paper. We have a reaction network with some entity A and a set of outputs for the autocatalytic core we're looking for, F. And we're wondering if there exists a core containing A and using foods from F only. And to answer that, well, you need to go from the most general formalization of the SAT problem. Here I just give one example, but in fact, there could be as many literals, so x1, x2, etc., and as many clauses as you want for phi. And then what we do is we reduce this SAT problem into the detection of such a core. And so this reduction, doing so, we build a reaction network, okay, that uses entities that mirrors the literals as well as the clauses. So here we have the target entity. We have the set of outputs that we identify. So they mirror the literals of the SAT problem. And crucially, we have this LC1, LC2, and CL3. I don't go into detail, but they make sure that if you have one solution, each solution of the SAT problem you have on the left correspond exactly to one autocatalytic core in the reaction network of the right. Okay, and so because we have this reduction, we know that the answer we are, the question we are asking is an NP-complete problem. So that's the sketch of the proof. And I won't go too much further. I would like now to talk about this realizability of those detected cores that now we detect using SAT solvers in not SAT solvers, SMT solvers actually, but in our paper. Okay, so what we mean by thermodynamic consistency of the network, which is thermodynamic consistency is in the title of the paper that we submitted.
May I interrupt you?
So it means that first we assume that the dynamics of the reaction network is driven by mass action kinetics. So once again, if I take these formulas like autocatalytic cycles, then mass action kinetics just says that the flows of reactions are given by constant rates multiplied by the concentrations. I mean, there's a question, apparently.
Yeah, exactly. So I have a quick question. Can you hear me?
Oh, no, it's okay. Sorry. I continue then. So multiply by the concentration of reactants, and for the backward reaction, that would be the product.
Il avait une question. Il y a pas le son sur. Ah, c'est qu'il y avait une son levée? Il y avait une main levée? Ouais. Ah,
C'est moi qui n'ai pas de
Raphaël a une question.
Vas-y, mets le son. Sorry, I don't have.
Like, can you hear me now?
Yeah, sorry, I forgot to turn
I
on the
see. Yeah, no, that makes sense. I just had a very quick question, which is back on the. I was just wondering, how do you encode the reaction network in those in the SAT problem that you said? Because the reaction network is given to us, right? Like, isn't the question that you have a reaction network and you want to see, given a food set, can you get, are some species autocatalytic? That's the question, right?
Yeah, so we just, sorry. So when we have the reaction network, we just say, okay, look for entities and reactions, and you write the inequalities that are given by this, these inequalities for any submatrix. And once you have found one in the reaction network, you tell the solver that you want to find another one that's not this one. And so you iterate this way until the solver does not find any more autocatalytic core. Does that answer?
Je peux ajouter un truc?
Yeah.
Oh, I was wondering, how is the information of the reaction network itself encoded in the clause that you had? Or is it not? That was the
Can I maybe add an element of answer to your question? Can you
Yeah,
hear me?
please.
I'm talking in
Yeah, okay.
Thomas' microphone. I guess maybe to answer your question, we have to clarify a point. One is how NP-completeness is proved, and the other is how we actually detect autocatalytic cycles in the system. So the proof is really what Thomas just described is a reduction. So actually it goes from SAT to autocatalysis. That's the direction we're taking. So we take a general formulation of the SAT problem and we translate it into the autocatalysis detection problem. And I guess your question is more about how do we actually encode the other way around, how do we detect autocatalysis using the SMT solvers? So this I cannot answer in the details. Denis would be much more able to do that, but maybe a piece of information is that we use solvers that are derived from SAT, but that are able to deal more efficiently with numbers, and they're called SMT solvers or constraint solvers more generally. And did you want more details on this?
No, that I think, thank you very much. That really clarified it. Please continue. Yeah, thanks.
Okay, so I was here, with mass action kinetics. Okay, so then what we mean by thermodynamic constraints, well, it means that each entity in the reaction network is described with a chemical potential, which is the sum of what in thermochemistry we call a standard chemical potential, or the Gibbs free energy, plus the logarithm of its activity, here identified to the concentration of the entity, okay? We also include activation barriers, so it means that between the reactants and the products, there's a transition state that you need to pass by, and then the concentrate is just the exponential of this difference between the transition state and either the sum of the reactants or the product side, okay? So when once you did that, you can actually show that, I mean, this is basic thermochemistry, that the reaction flows can be written with the exponential of the chemical potential only. And we remind that there's a quantity in thermochemistry called the affinity, which is merely the difference between the chemical potential of the reactant side and the product side. So for the first reaction, it would be mu E1 plus mu E2 minus mu E3. And you can see right away that they have the same sign. And actually a constraint that is imposed by the second law, because the product of phi and the affinity is proportional to the irreversible production rate of entropy, of irreversible entropy, sorry. Okay. So this is how we make the reaction network thermodynamically consistent. But now the question is, do the cores that we detected with the solvers we're using, with the constraint given by Rx, that we call potential autocatalytic core, because we don't know if there exists a region in the concentration space where they can be realized. So the question we're now addressing, if this is the existence of a vector of concentration C, such that Si constant phi, but which depends on the concentration with Thu March action kinetics, is strictly positive. And if such a vector C exists, we call the cores that we detected consistent. So once again, I just gave the sketch of the proof. In fact, we use the formulation that we found in the previous slide, that we can write the reaction flows with the exponential of the chemical potential. And actually, this exponential of chemical potential turns out to be the right variables to work with in order to do the demonstration. And so, in fact, we found a pack witness that's VR1, VR2, VR3 here, and we want to achieve it. And so the situation is that we have n nonlinear equations with more than n variables, okay, the core entities plus the food and the waste. So it's sub-constraint problem, but because it's nonlinear, we don't really know if a solution will exist anyway. And just by looking at the situation here, we can already answer something interesting. It is if we know that a potential autocatalytic core is consistent, meaning that there exists a region in a concentration space where it can be realized, then you know that varying the free energies of the entities cannot make it inconsistent, because we are identified that the correct variable to work with is the chemical potential, actually, and not the concentration. And so if you vary the Gibbs free energy, Gi, then you can always compensate with a movement varying the concentration of the entity. Okay, so that's the second big result of the paper, the second theorem here. It's a bit technical, so let's go slowly into it. So it says that if we have found a core witness, so a vector of flows that tells you that this network is an autocatalytic core, then we know that there exists some lambda strictly positive and some concentration vector C such that lambda V is induced by C, okay? So it means that if you have some witness, you can achieve it up to some proportionality factor, okay? So it might be very small, but it's non-zero. So you can achieve any witness. And I mean, there's just one step to go further. We need to realize that lambda times V is still a core witness, because the constraints that need to be verified by VR1, VR2, VR3, they come from linear algebra formulation of X. So this is all linear. So if you multiply by a constant, all the inequalities would still be respected. And so that allows us to conclude that all the cores that we detect are thermodynamically consistent. And so, oops, sorry, this is, okay. So we go one step further by saying that now if we study sets of cores, they can become incompatible for several reasons. One of them would be that two cores sharing one reaction ask for the shared reaction to run in opposite directions. So there does not exist any reaction flow that allows to make the cores run simultaneously. But we also found an interesting type of incompatibility, which we call thermodynamic incompatibility on the right. And in fact, you could convince yourself that the two cores on the right, they are compatible on topological grounds. You mean that you can find reaction flows that allow the cycles to run simultaneously. But once you inject mass action kinetics and thermodynamic constraint, it's not the case anymore. And that's something we're still trying to better understand this, how this can occur with a master student that recently joined us, Iris. And that's all for me. I now give the talk back to Sylvain.
Yeah.
Sorry, I need to stop sharing.
Là, vous m'entendez? Can you hear me?
Yeah.
Okay, great. Now I can't go between slides. Ah, c'est le partage. I will stop sharing and share again because it didn't work. So I've got, yeah, another 5 minutes if that's okay.
Yeah, please continue.
Okay. So yeah, this was a quite complete description of the paper. And I'd like to, I'm trying to get to my next slide, but for some reason, it's not working. Some very obscure reason. Okay, let's do this. This. And this.
Bizarre, c'est ça qui s'ouvre.
I have no idea what this screen is. I can see a white thing that you can probably see as well.
Ah, on voit que ça.
It's not my.
Sinon, regarde. C'est en présentation. Ouais. Il n'est pas après l'écran.
Super chelou, hein? C'est le partage qui fait ça.
C'est une présentation différente.
Now it's working. Great. Okay, sorry. So
after this work, we started realizing, like others actually, that in these physical soup, there could be some interesting interactions between autocatalytic cycles that could drive not directly evolutionary dynamics, but already ecological dynamics. And it actually strikes us that ecology may have preceded evolution in that sense. And Thomas just described this concept of incompatibility or compatibility between cycles. What is meant here is that two cycles are compatible if they can run together. And if they can run together, maybe they can interact in either synergistic or antagonistic ways. Okay, started again this little problem. Now it's working. So here is an example of two cycles, the black and the white one. I won't go into the details, but the dashed arrows are the ones that lead to an interaction between these cycles, which in that case is actually an antagonistic interaction that drives interesting dynamics. There can be many other forms of synergistic or antagonistic interactions that we are currently investigating. To actually go further into this analogy with ecology, what we want to see is whether we can retrieve typical ecological dynamics and perhaps borrow very efficient methods that have been developed within theoretical ecology that often have very strong links with non-equilibrium physics as well. And one of the interesting aspects of these ecological interactions is that they may drive multi-stability. And I will try to convince you that multi-stability is actually a crucial concept in this context. This particular set of cycles actually drives bistability. These two cycles are bistable, and this is due to some antagonistic interactions between them. So what do we mean by bistability or multi-stability in general? I'm sure most of you are aware of the concept already, but here is just a little drawing, a phase diagram showing, okay, what happens if you start from different points in the space of concentration of the entities of the system. That's just a toy model. It's not actually autocatalysis that's driving this, but multi-stability is the situation where, depending on where you start from, you will reach different stationary points. And you can also represent things in this way. Imagine that you have something rolling on a landscape, and you can have attraction basins that can be more or less large. In that case, the blue attraction basin is bigger than the red attraction basin, which means that the blue state is going to be more robust than the red state. If you shake the system, if you introduce random perturbations, the system is going to remain for longer in the blue state than the red state. And we anticipate that the transitions between the two states could well be the very fundamental way of understanding mutation that are very important to biologists. And I will try to explain that a little bit better with this next slide, where I describe the way we want to investigate the implications of this multi-stability on metasystems composed of many subsystems, each occupying particular patches. So we would have patches, each containing a system as Thomas just described, but introducing the possibility of flow of matter between these different patches and looking at the consequences of this. One thing we anticipate is that if we don't have flux among neighboring patches, obviously it's just the robustness, so the size of the attraction basin basically, that is going to drive the proportion of blue and white patches in the system. But if we introduce connection between the patches, it may well be that some locally stable systems, although they are not the most robust, they don't have the biggest attraction basin, they are actually more prolific, perhaps because they produce more matter, perhaps because they are more able to integrate faster some very high energy but unstable components of the system, for example. And it could be that they're actually better at spreading across space, although they are inherently less stable than the others. And to us, this is an interesting contrast to be made between robustness on one side versus something that could perhaps be called fitness already, which is the ability to spread even though you're not inherently more stable than others. And typically, living beings are not very stable generally. but life as a whole is something very stable that has been lasting for 4 billion years. So with this, I will just end with some little parallels that we're trying to draw that are just speculation at that stage. And basically, we're trying to understand how the concepts we're encountering in those models could be related to these much higher level concepts of evolutionary biologies. Perhaps those patches are to some extent individuals within a marginally Darwinian population. The population would be the entire grid in the system. Obviously, this is a bit far-fetched because individuals could potentially be some components of the system, but not all, because at the moment, we basically don't know how to differentiate environment and individuals. But that's a parallel that we're working on. Another interesting point is that we could conceive reproduction here as just the transmission of a configuration between neighbors. And that's, to us, another interesting insight of those models. It's a different way to understand reproduction. And finally, as I was saying, mutation could be seen as shift among those locally stable states. Basically, it's those shifts that produce the variants that could be called heritable variants in this context, and that may drive interesting Darwinian dynamics. With this, I'm going to end. Thank again our collaborators, Denis and Etienne in particular, because you haven't seen them yet, but they might answer questions with us. Thank you very much. And we'll take questions, obviously.
Yeah.